Hey, welcome back to week 7, Graduate Statistics, University of Cincinnati. So we just finished talking conceptually about the confidence interval, that it helps us get an interval estimate of a parameter of the population versus a point estimate, which increases our confidence that we are getting it right. Though it reduces precision, but it increases our confidence because now we have an interval that we expect to include the mean with a particular level of confidence. And I showed you how the central limit theorem can be exploited to actually get and compute that confidence interval from our data. Now I want, before we move on and learn how to compute it specifically, to check your understanding of the concept. So let's analyze this particular statement. Among all 18 to 34-year-olds, fully half or close to half, 49%, say that they have taken a job they did not want just to pay the bills. The standard error associated with this estimate was 2.2%. That's the expected variation of the mean computed by taking the standard deviation of the sample divided by the square root of the sample size. Results were obtained from a sample of 2048 individuals, 2048 individuals. Which of the statements below are false? Or which is false? A higher sample size would yield a lower standard error. If you thought true, you're right, because the standard error is equal to the standard deviation of the sample divided by the square root of sample size. So if we have a larger sample size in the denominator, the number that will come out will be smaller. The margin of error, that's B, the margin of error for a 95% confidence interval for the percentage of 18 to 34 years old who have taken a job they did not want is roughly 4.4. If you thought true, you're right, because the margin of error is the mean plus or minus 2.2. So the total margin of error will be 2 times the standard error, approximately, for the 95% confidence interval. And that comes from the 68, 95, 99 rule, that approximately 95% of the data is between plus or minus 2 standard deviations. If the standard deviation of the sampling distribution, which is the standard error, is 2.2, then the margin of error will be 2 times that. The 95% confidence interval for the percentage of 18 to 34 years old who have taken a job they did not want is roughly 4.1 plus or minus 2.2%. This one should be false if you said true to this one, because it would be 41 plus or minus 2 times the standard error, right? Not 1 time. This would be if you wanted a confidence interval of 68%. If you wanted to be just 68% confident that your interval would include the mean, then that would be your guy. So D by default is true, but let's analyze that. The 99.7% confidence interval for the percentage of 18 to 34-year-olds who have taken a job they did not want is roughly 41% plus or minus 6.6%, and that is true because of the 68, 95, 99%, 99.7% rule that says that about 99.7% of the scores will be included between the mean plus or minus 3 times the standard deviation. All right, so this number D is true. So the statement that's false here is actually C. So confidence interval, let's look at the general formula for it. The confidence interval for a population mean is computed as the sample mean plus or minus a margin of error, which is computed by a critical Z value that will provide the margins for the middle X% of the normal distribution times the standard error of the sampling distribution, which is the standard deviation divided by square root of n. All right, and that X value here could be 90%, 95%, 99%, etc. We will unpack this in the next slide. But the idea is that this Z needs to be the Z value that will form the boundaries for the middle 90% if you want a 90% confidence interval, 95% if you want a 95% confidence interval, 99 if you want a 99% confidence interval. We'll see how we'll get the Z. And again, in order to be able to do that with the data from a sample that you got, you need to make sure that your sample meets, your data collection meets the conditions for the application of the central limit theorem, which is independence. You need to have a sample that has independent observations, and your sample size should either be large enough such that if the distribution is skewed, you still are okay, or if the sample size is not that large, that the sample, the distribution of the population of the data in the population should be normal. All right, let's see how that is computed. Let's see how we get this Z value, right? We know how to get the mean. We can just compute the mean from our sample. We know how to get the standard deviation from our sample. We know the sample size. So all these three pieces here are easy. Now let's think about how to get that Z value in order to get our margin of error estimated. So imagine we want a 95% confidence interval. We want then the Z values that will be the boundaries, the minus Z value and the positive Z value that will be the boundaries of the middle 95% of my data, because I want to be 95% sure that the mean will be inside of there, right? So what is this? Oh, is it not -2 and +2? It's roughly that. That's where the rule comes from, but it's not quite precisely that. So how do we compute these Z values? First of all, we need to understand that because it's symmetric, 95% is in the middle. That means that we have two pieces of equal size, and those sizes will be 1 minus the 0.95 divided by 2, which equals 0.025. So I have 0.025 on this side and 0.025 on this side, which means that this negative Z will be related to the percentile 0.025 or 2.5, and the percentile here will be the 97.5th percentile, right? So how do I get that? Well, I can use the Q-norm function that you're used to, that if you give the percentile, you get back the Z-score, right? The score that forms the boundary here. So almost 2, not quite 2, it's negative 1.96 here. Because this is symmetric, we know that it will be positive 1.96 there. All right, so to compute the margin of error for a 95% confidence interval, here's the formula. I'll get the mean plus or minus 1.96 times the standard deviation divided by square root of n. Okay? Now, what if you want to compute, what's the formula for computing the 90% confidence interval? Well, for the 90% confidence interval, now I have 10% to divide on the two sides, right? So I have to find the boundary. So 1 minus 9.90 divided by 2. So I have 0.05 on this side, 0.05 on that side. So we want to get these values of Z, which I can again get by getting the Q-norm of the percentile, 0.05, and it's negative 1.64. So those are the boundaries. So if I were to get the formula, I keep being in the way, it will be the mean plus or minus the Z critical, which is the Z that forms the boundary that I want, 1.64 times S, which is the standard deviation divided by square root of n. Of course, you can get the z's also by looking at tables like this, but we are more sophisticated than that nowadays, and we don't need to pull out those tables. But if you wanted to, that's probably the way you learned. If you want to get the probability, the z-score related to the 0.025 percentile, get it here, the z will be negative 1.96. So one part of the number is here, the other part is there. So that's where the 1.96 come from. But again, you don't need to use tables because we have R in this class. So what does the confidence interval really mean? What does it really mean to have a 95% confidence level? I've been repeating this multiple times, but I want to illustrate. It means that if we took multiple samples and built confidence intervals for each sample using the equation, 0.8 estimate, say the mean, plus or minus 1.96 times standard error. Remember, 1.96 are the z value, the critical z that embraces 95% of the distribution. If we were to compute these over and over again, imagine this is the true mean, and we decided to get 25 samples. I compute the estimate, the confidence interval for sample number 1. I compute the confidence interval around the mean for sample number 2. I compute the 95% confidence interval for sample number 3, so on and so forth. What does it mean to have a 95% confidence interval? It means that 95% of those will cross the true mean of the population. So the true mean of the population is not jumping around. It exists. If we are trying to fish in murky water with a stick, we would be just computing the point estimate every time. And we would be missing it the majority of times, right? So we got it right twice in this situation. So what we want is a net. So our confidence interval is a net. So if I sample multiple times and I throw the net every time, almost every time I get my fish, right? 95% of the times I get my fish right. Okay, so 24 of these intervals out of 25 is 0.96. You can do this through simulations if you would like, let me know and I can get you code. But that's the idea of what a confidence interval is, okay? Sorry. So if we want to be very certain that we capture the population parameters, should we use a wider interval or a narrow interval? If you're thinking a wider, you're right. So to increase the chance of getting a fish, the wider the net I cast, the greater the chance I have to get the fish. Now, that kind of makes sense, right? So the more I extend my interval, the larger it is, the greater my chance of that interval, including the mean, each time I compute it. So you increase your accuracy. You increase your chance of including the mean when you get a wider interval. So you might be wondering, why in the name of the Lord don't we just compute 100% confidence interval or 99% all the time? Well, this is similar, again, to asking what is the cost of building a confidence interval with greater accuracy? What's the trade-off, I'm asking? So think about this. Imagine you looked at the weather forecast today, and it said that the low temperature, that the temperature today would be somewhere between -20 Fahrenheit and 110 Fahrenheit. Somewhere between the two. What is the chance of this report being accurate? Very, very high, right? It's very, very high, the likelihood that the temperature will be somewhere between -20 Fahrenheit and 110 Fahrenheit. However, what are we losing? We're losing what we call precision, right? Because we have no idea even what clothes to wear if the weather can go from -20 to 110. So every time I gain in accuracy, I lose in precision. So it is important to get like a good trade-off between the two, and 95% confidence intervals typically give you that trade-off if you have a large enough sample such that your standard error is not that big. Okay? So this is it for the computation of confidence intervals. We'll come back next to finalize and give some examples of how to apply that. See you soon.